Hello viewers, in this video we are going to talk about the semiconductor physics. In last video we have seen the formation of energy bands using the chronic penny model, and in this model we will extend it to semiconductors. Basically semiconductors are insulators at absolute zero with the gap between conduction and valence bands of the order of 1 electron volt or so. So at room temperature, this 1 electron volt order energy gap between conduction band and valence band is easy to overcome by the electrons of the semiconductor, and hence they have some non-zero conductivity at room temperature. Though they are insulators at absolute zero, they behave just like partial conductors at room temperature. So this is the reason for finite conductivity of semiconductors at room temperature. And basically semiconductors, the natural semiconductors, elemental semiconductors, they exist to the they actually belong to the fourth group. The elemental semiconductors best examples are silicon and germanium. Silicon and germanium are the elemental semiconductors. They belong to the fourth group. Actually, by combining the third and fifth group, one can make compound semiconductors. So third group elements like gallium, indium, etc., and fifth group elements like phosphorus, arsenic, etc., if you combine, you are going to have gallium arsenide, indium phosphide, etc., compound semiconductors. Similarly, with the help of second group and sixth group combination also, one can make compound semiconductors. That is beyond the scope of this discussion. We talk only about the elemental semiconductors, and let's define what is intrinsic semiconductor. Generally, intrinsic semiconductors are the purest form of the semiconductors. If you take the elemental semiconductor like say silicon or germanium, in intrinsic case, the purity of the sample is almost close to 100%. So in reality it may be 99.99% or so. So they do not have any impurities present inside, and hence they are called intrinsic semiconductors. Mathematically speaking, if the number of electrons in conduction band and the number of holes in valence band, if they become equal at any non-zero temperature, one may call it as intrinsic semiconductor. So in intrinsic semiconductor case, at any non-zero temperature, there are equal number of holes and electrons. This concentration of carriers inside semiconductor is very poor, and if you take silicon, it's of the order of 10 power 10 number of carriers. Carriers means either electrons or holes. 10 power 10 carriers per centimeter cube of a pure semiconductor crystal. It is silicon. If you take silicon, it is 10 power 10 per centimeter cube, and if you take germanium, typically it is going to be 10 power 13 per centimeter cube order. 10 power 10 for silicon, 10 power 13 for germanium at room temperature per centimeter cube of the crystal. If you consider any excellent conductor, the order will be around 10 power 27 to 10 power 28 30 order. 10 power 28 order per centimeter cube carriers will be available in case of excellent conductors like silver, gold, etc., metals. So these semiconductors at room temperature, though they have non-zero number of free charges, their conductivity is really very poor at room temperature. And if we use them as it is, we may not find it useful. So the conductivity must be tuned or enhanced through several mechanisms. One such mechanism is the process of doping, means addition of controlled impurities. So under controlled conditions, the pure semiconducting sample will be added with known quantity of impurities. That is what you call as doping. So doping is one case in which the conductivity of the sample increases, first way. And there is a second way in which heating of the sample also increases the carrier concentration, but it is not always possible to maintain high temperatures for the semiconductor. This is not a very famous method. And the third method is through photo induced carriers, means whenever one shines electromagnetic radiation on the semiconducting sample, some of the holes and electrons are ejected. So this is also a way to increase the carrier concentration, but this is also not advisable always to enhance the conductivity. So the best method is by doping one can enhance the electrical conductivity. So if you do the doping, it results in extrinsic semiconductor. Extrinsic semiconductors are those semiconductors where there are unequal number of holes and electrons at any given temperature. So if you take any semiconductor which is extrinsic, there unequal number of holes and electrons will be present. If the number of holes per unit volume are dominant compared to the number of electrons per unit volume of given semiconductor, we call the p-type semiconductor. Of course, p, the holes are majority because hole number is more, electron number is less per unit volume. We call it as a p-type extrinsic semiconductor. Same thing is applicable to n-type also. In n-type, we have excess number of electrons per unit volume compared to number of holes available per unit volume of the semiconductor. That is the n-type semiconductor. And usually to get this p-type semiconductor, one has to dope trivalent, that is the group 3 elements like aluminum, bismuth, gallium, indium, etc. to this intrinsic semiconductor to make it p-type. So third group addition makes the sample a p-type, and similarly fifth group addition, the pentavalent, sorry, there is a correction, there is a pentavalent group, fifth group, nitrogen, phosphorus, arsenic, antimony, etc. So all these elements, if you add all these elements, any of the selected element, if you add to the intrinsic semiconductor, one can obtain the n-type semiconductor. So in n-type you have majority electrons in the conduction band. In p-type you have majority holes in valence band. So at absolute zero, if you consider the p-type semiconductor at absolute zero, we are going to have non-zero number of holes in this semiconductor. Usually if you take intrinsic semiconductor at absolute zero, there will be 0 electrons and 0 holes because their number is equal, and at absolute zero it's not a conductor, so it is 0. Whereas if you hypothetically imagine the p-type semiconductor at absolute zero, as there are excess number of holes, so the net charges in this p-type is non-zero even at absolute zero, and p will be, the holes will be more in number even if the electrons are 0. And same logic is applicable to n-type. If you consider this at absolute zero, there will be non-zero number of free electrons even at absolute zero for n-type semiconductor. Let's have the discussion of carrier concentrations. First we start with intrinsic semiconductor. So in intrinsic semiconductor, how many number of electrons are going to exist inside the conduction band? That is what we are going to discuss in this article. Generally, to count the number of carriers, one has to adopt the statistical method. That is, one has to know how many allowed states are there inside the given conduction band and what is the probability of occupancy of each and every state. If one knows both of them, then one can proceed by multiplying the density of states with the probability of the corresponding state. One can get the carrier concentration. The idea is simple. A simple example of class. If the class contains roll numbers from 401 to 460, the total number of students inside the class can be counted in the following statistical manner. Normally, one can count the heads individually, but as we are dealing with atoms inside a solid, it is not possible to make the head count physically. So, probabilistic manner is really required. So, what we do is in the class, what are the allowed roll numbers? First, we will find out 401, 402, 403, etc., up to 460 is the allowed roll numbers in the given class. Of course, common sense says that 401 is one state, 402 is another state, but we don't know whether there is any 401.1 state, 401.2 states, etc. There may be possible inside the solid. So one has to know what are the allowed states inside the given solid. So that is described by the density of states function, which we have already derived in the quantum free electron theory in the earlier videos. So this density of states describes the allowed states, and we have also discussed the Fermi-Dirac distribution function, which actually describes the probability of occupancy of a particular state by an electron. So f of E, the Fermi function, was a probability function. So when the allowed states are multiplied by the corresponding probability, in our classroom example, assume that roll number 401 is present with 90% probability. So I'll go to that particular state, and in that state I'll put a 0.9, 90% probable. And I'll come to the next allowed state, which is 402, and I will multiply by the corresponding probability. Let us say that that particular student is irregular. Let us say 50% present. So in that case, I'll put 0.5 in the 402 seat. Similarly, 403 maybe 70% present. So I'll put zero point 0.7 in the third seat. Like that, I'll go to 403, 404, 405, 406, so on up to 460. So if the class is from 401 to 460, if I do this probability of all seats, and if I add all the probability, if you recall 401 I said 0.9, so 402 I said 0.5, so 0.9 plus 0.5, and then third one is 70% I said, so it is 0.7. Like that, if you keep on adding from 401 to 460, that is going to tell us how many number of students are present inside the given class in a probabilistic manner. So here we proceed in a similar manner. So we'll first try to find out what are the allowed states inside the given band. So in our case, the classroom is nothing but the conduction band of the solid. So that conduction band has some limits. So conduction band may be having a conduction band edge EC, and it may extend up to some top level which is not known to us. So if you just count the probability of occupancy of electron from the EC till the maximum allowed state, and add all of them, that is going to give us the number of electrons per unit volume inside a given conduction band of a semiconductor. So this is the exercise. So what we are going to do is, if you recall this Z of E, dn by dE is Z of E, or if you pull this dE this side, it is going to be dn equal to Z of E dash times dE. There is a reason for writing this dash or prime, because these E dash are not calculated properly in the earlier quantum free electron theory. We will come to the correction a little later. So for the time being, you call it as some Z of E. So this dn is nothing but the density of states multiplied by dE. What does this dn represent? If the number of electrons which are existing, number of electrons means number of electron states, number of electron states that exist between n and n plus dn, n and n plus dn. So that number is given by the density of states at E multiplied by the energy interval, that is E to E plus dE. If there are dn electrons which lie between E to E plus dE energy, total energy inside the given solid, then the dn is related to density of states multiplied by dE, like this. Okay, so if one has to find out the total number, actually you have to multiply by the probability function. Normally you can take this number directly, but it is actually allowed states. In our classroom analogy, there is no need that all the 60 students must be present. If the college gets less intake, the allocated seats are 60, but there is no guarantee that all the 60 seats are filled. If at all the intake is less, if the students are less in number, instead of 60, let's say some 50 seats got filled. In that case, the topmost filled seat will be 50 instead of 60. So one cannot just count the total number. So what are the actual number is described by this probability function. So these are the allowed states, and this is the probability of their presence. So probability of presence multiplied by the allowed state is going to describe the number within this infinitesimal region, n to n plus dn. So this dn is representing the number of electrons inside the conduction band within the limit E to E plus dE. This is the expression. Please remember this, we will be using it later in the case of holes in valence band also. As we know, this Fermi-Dirac distribution function earlier in quantum free electron theory, we have derived this. Let's make an odd representation of that. Earlier, we have seen the step function in a different manner. We have plotted the vertical axis as the probability and the horizontal axis as the energy. Here the axis got interchanged because most of the literature will follow this rule. So if you just flip the axis, you will be back with the same Fermi-Dirac distribution function which was discussed in the earlier video. So at any temperature other than absolute zero, this normal step function, you can see here this step function, it won't go in a manner like a step, it will just get some kind of steep. So if you consider this, actually up to EV, the electrons are filled. Of course, these electrons are not electrons, they behave like holes. In the previous video of effective mass of electron, we have seen that the top edge of any band will have holes, the bottom edge of any band will have electrons. So if you look at this EC, this is the bottom part of this band, so the bottom part will behave like electrons, whereas the top part of this band will behave like holes. So you can clearly see that this solid line is predicting the probability of electrons. So here there is a shortage of probability, means at absolute zero until this point they are ideally filled, but at room temperature some of the electrons are escaping, that's why the probability is decreasing, and this high energy tail portion of this Fermi Dirac distribution function is encroaching into the conduction band. Normally the probability was zero at absolute zero, but because of these vacated electrons, this tail is encroaching into this region, leading to a non-zero probability here and leading to an absence of electron, which is the presence of hole here. Or equally, one can sketch the probability of hole this way. So if this is representing the probability of electron, the solid line, the probability of hole is depicted here. So the probability of hole will be there in this region. So you can use the expression in calculating the concentration of holes in a later exercise. So for the time being, let us focus on this particular axis. So this is depicting the probability of electron. Okay, now as we said, there must be some correction to this Z of E. Earlier it was Z of E, the density of states. Now we are adding some prime, some dash to this. The reason is, while calculating the density of states, if you recall the quantum free electron theory that we have discussed in earlier articles, that the density of states expression was derived on the basis of E versus K relation, which was a parabola. If you recall, the E was E equal to h cross square k square by 2m, which was a parabola in the case of free electron theory. But after band theory, we came to know that it is not a perfect parabola, but it is some kind of split parabola. So if we make this parabolic approximation that even in this band it is roughly equivalent to parabola, you can apply the same density of states. The density of states was derived for the case of metals actually, but we can still use it for the case of semiconductors by assuming this as a parabola, but with one correction. While deriving that expression, that E equal to h cross square k square by 2m has the lowest energy, that is the base point which is shown here was 0 there. But in our case, this is not 0 because it is the conduction band edge. If you look at this picture, this region is representing the conduction band and this region is going to be valence band, right? So there is a gap between, which is what you call as Eg, the energy gap. So in the conduction band, it was a parabola which is not sitting at the 0 value, but it is rather sitting at the EC value. So one has to make some manipulation. So whatever we called as E dash, the so-called new density of states, you can see here this is E dash. So this E dash is actually counting energies on the parabola. So if you choose any point on this parabola, that energies are measured with respect to this dotted line. So it is taken here, that's why we are calling this as E dash. But actually, if you take the 0 level somewhere here, the same energy you may call as some E. So this point with respect to this is E dash, this point with respect to 0 is E. So from 0 energy level it is E, from conduction band edge it is E dash. If you choose this dotted line as EC with respect to ground, mathematically you can easily prove that EC plus E dash is this E. So I repeat, EC plus E dash is equal to E, which we are going to derive in a moment. And same logic is applicable for valence band also. If we are using the energies in the valence band for calculation of holes, the energies here are once again measured with respect to this edge because it's another inverted parabola in the case of valence band also. So this inverted energies once again are measured with respect to EV but not with respect to 0. So one has to do the same subtraction to get the E dash corresponding to valence band holes. That we'll do later. So the same Ni, as we know, this is the conduction band and we don't know the top of the conduction band where it ends. So what we have to do is, in order to get the total number Ni, this dNi must be integrated from the lower energy, that is Ec, till the top of the conduction band. So that is Ec to top integral over this dNi is nothing but f of E z of E dash dE. So this top can be safely extended up to infinity, because I don't know what is the topmost field energy level. So by making this infinity, are we doing anything wrong to the integral? Of course not. Why? Because this f of E is taking care of this infinity. Even if you take the energy tending to infinity, this f of E is not going to blow up, but rather it drops to 0. You can easily convince here. So as you increase the E in this direction, if energy goes to infinity, simply the probability drops to 0 beyond a certain value. And hence, if you multiply this z of E, however big it may be, this f of E drops to 0, and hence the integral becomes finite beyond a certain value of E. So we can mathematically safely extend this up to infinity. So this is the first part. Now let's come back to the substitution. Here we are going to do that. You can see this f of E, we have substituted E minus EF by kBt plus 1. We know the Fermi function, 1 by exponential of E minus EF by kBt plus 1. This function, if you calculate the value at room temperature means 300 Kelvin. We know this Boltzmann constant is Kb, which is 1.38 into 10 power minus 23 joule per Kelvin. So its order is 10 power minus 23. If you take T as 300, you can write it as 3 into 10 power 2. 10 power 2. So this is 10 power minus 9 minus 23, and this is 10 power plus 2. So its order is 10 power minus 21. So the denominator is going to be something like 10 power minus 21 at room temperature. And typically the E minus EF, these energies are of the order of electron volts. Electron volts. Why? Because we know in semiconductors, the gap between conduction and valence bands cannot be harder than a few electron volts. So it's typically 10 power minus 19 joule, because electron volt can be expressed as joule by multiplying with 1.6 into 10 power minus 19. So this numerator can be safely taken at room temperature as 10 power minus 19. So this is 10 power minus 19, and this is 10 power minus 21. So minus 19 minus 21, as 21 goes to the numerator and subtract the 19 from that, it is 10 power 2. So typical value of this is something like 100 or 100 order. So it is e power something like 100. E power 100 is usually big number. So no matter whether you add this one or subtract or neglect, it is not going to make any sense. So you can simply neglect this. It is just 1 by e power something. Okay. So after that approximation, we can write 1 by exponential of this, or you can safely take it to the numerator by writing this negative sign. Okay. This is approximately the f of e. Therefore, the z of e dash with the above mentioned approximation, that if you replace this e dash with e minus ec, we are going to have z of e dash, the density of states. This expression you can refer to the previous video on density of states, we have derived there. So this z of e dash is equal to 1 by 2 pi square. There it was 2m by h cross square. There was no me star. As we are dealing with electrons in conduction band, we are just using a subscript e. For hole we use h or p. The star is because it is effective mass. It's not the real mass, because the electron's mass is going to vary inside the band. So we use this me star, not as me or m, and remaining is same. Of course, this e dash, in the earlier case we called it as e. Now we use this e dash as e minus ec. You can see e dash equal to e equal to e dash plus ec, or e dash equal to e minus ec. This we have already explained in the previous part. So this, if you substitute here, this bracket term, of course, it's mathematically difficult to carry. So we are denoting it with some gamma. There is no specific meaning for this gamma. It's just a mathematical constant. Only for carrying this big number, we are just putting this gamma. Apart from that, there is no physical significance. So this gamma, of course, equivalent to 1 by 2 pi square of this, and e dash is becoming e minus ec. So finally our z of e in terms of e, not as e dash, our z of e will be just gamma times of e minus ec square root. So this you can substitute earlier in the earlier integral, as the integral was EC to infinity dni, which is nothing but f of e gamma times of e minus ec power 1 by 2 de. As f of e we have proved as 1 by this simplified to exponential of minus of e minus ef by kbt. This is the simplified version. So we put f of e like this, and we put z of e dash like this. So after substitution we can get this as this. Simple substitution. Now we need to simplify the integral. This is the tedious task. So in order to get rid of certain terms, and in order to make it look like some gamma function, as in mathematics you have been taught the beta function and gamma function, we will be using the gamma function here in a moment. So here let's substitute e minus ec by kbt as some y. It is only for integration simplification, so we are just putting this as y, and we take de is equal to, of course let's differentiate this, de is equal to kbt goes to the other side as kbt dy. As ec is a constant, its integration becomes 0, its differentiation becomes 0. So e de is equal to kbt dy. Keep this. Now after change of variable, one has to substitute the upper limit and lower limit. So if you put e as the upper limit infinity, it is going to be y equal to infinity minus ec by kbt, which is just infinity. And if you substitute the lower limit as ec, which is going to be ec minus ec by kbt, the lower limit 0. Now the integral after change of variable, gamma is constant with respect to de, so it can be pulled outside, the gamma comes outside, 0 to infinity. Now for e minus ef, this e has to be replaced. If you look at this expression, it is going to be e equal to y kbt, kbt goes there, plus ec. So instead of e, one can write y kbt plus ec. So we have substituted the same here, y kbt plus ec, this is e minus ef by kbt. So minus of this already we can see it is a minus of e minus ef by kbt. So substituted. And similarly for this e minus ec, as we know e minus ec by kbt is y, so it is going to be y kbt under root. So this is y kbt power 1 by 2. And last one, instead of this de, one can write this kbt dy, because it's already seen here, in place of de you can write kbt dy. So let's substitute it here, as this kbt power 1 by 2 and kbt becomes kbt whole power 3 by 2, which is also constant with respect to integration, it can be pulled outside. So gamma times kbt power 3 by 2, and also in this part, apart from this y, remaining all are constants. So if you expand this term, minus y kbt by kbt, it is just e power minus y, and the rest of the term is minus ec plus ef. So it is ef minus ec by kbt, exponential of ef minus ec by kbt. So this is the same, exponential of ef minus ec by kbt. It is also a constant, so we are pulling it out of the integral, and the final part of the integral is 0 to infinity e power minus y, y power 1 by 2 dy. Actually this is gamma function, so you can actually write this as gamma 3 by 2 minus 1. Sorry, I can include this in a bracket to make it look better. Okay, so this term basically is representing a gamma function, which is gamma 3 by 2. E power minus y, y power n minus 1 is gamma n. I repeat, e power minus y power n minus 1 with the integral running from 0 to infinity is called gamma n. So it is, in place of n we got 3 by 2. So this is going to be gamma 3 by 2. So this gamma 3 by 2 is further simplifiable using the simple calculation. There is an identity in gamma functions. Gamma n is equivalent to, sorry, gamma n plus 1. Gamma n plus 1 is equivalent to n gamma n. I repeat, gamma n plus 1 is nothing but n gamma n. So if you take this 3 by 2 can be written as 1 by 2 plus 1, and this is our n. So n gamma n is this, and the constant is already known. Gamma half is always root pi. It is taught in the special functions of mathematics course. So this is root pi and this is 1 by 2. So it is going to be just root pi by 2. This is the expression. So finally, this integral becomes gamma times of k by t power 3 by 2 exponential of this into root pi by 2. So the same function, now gamma is replaced with its value into root pi by 2. So this is the ni. It can be further simplified by writing like this. So if you take this 2 separately and pull this kbt inside, of course this was h cross square. H cross square can be written as h by 2 pi whole square. So which becomes h square by 4 pi square, or in other words, as it is under the square root, you can take it as 2 pi outside. So 2 pi square is gone, so it is 2 pi cube. So this goes to the numerator as 8 pi cube. So 8 pi cube, if you take a closer look here, 8 pi cube, and this is root pi, this is pi square. So 8 pi cube divided by 2 pi square. So 1 pi remains and this 2 goes there and 4 remains. And this 2 gone, so we have 2 in the numerator. So 2 into 2me star power 3 by 2 by h square, and 1 pi remained in the numerator with along another root pi. So pi root pi is nothing but pi power 3 by 2. So this pi also can be safely pulled inside. So it becomes 2 into 2 pi m e star, and kbt is also under 3 by 2. So kbt comes inside. So 2 m e star 2 pi m e star kbt by h square whole power 3 by 2 will be the function along with a multiplicative constant 2. So that is the expression here. And finally, this whole term one may call as NC. So if you take this as NC, NC is another constant, conduction band constant. So this constant, if you write like this, you are going to have Ni, the number of electrons inside the conduction band per unit volume of the given semiconductor, as Nc times exponential of minus of Ec minus Ef by kBt. So this expression is for number of electrons in conduction band. Proceeding in a similar manner, one can obtain the concentration of holes in valence band. That is the next article.